You know, high-strength aluminum, it's the backbone of modern aerospace. It's incredibly light and super strong. But there's always been this one massive catch. If you try to weld it using traditional methods, you're just asking for trouble. For decades, joining these advanced alloys has been a huge engineering headache. But today, we're going to look at a totally revolutionary process that completely changes the game.
So what's the big deal? Why is it that when you take one of these amazing high-performance aluminum alloys and hit it with a welding torch, the whole thing just fails, often catastrophically? And look, this isn't some new issue. It's a deep, fundamental challenge that has had engineers scratching their heads for a long, long time.
Well, the villain in this story has a name. Actually, it has a lot of names, but we'll get to that. The big one is hot cracking. This is the nasty defect that shows up as the weld is cooling down, and it just completely wrecks the strength of the joint, sometimes before it's even fully solid.
Okay, so let's really dig into this cracking problem. Because if you don't understand why things fail, you can't really appreciate the elegance of the solution. And we're not talking about some minor little flaw here. This is a massive issue that has seriously limited how we can even use some of these incredible materials.
I mean, this problem is so common, metallurgists have a whole bunch of names for it. You got hot cracking, hot tearing, solidification cracking, shrinkage brittleness, the list goes on. But whether you call it one thing or another, they all point to the same disastrous outcome. A weak, cracked weld that you just can't trust.
So how does this actually happen? Well, picture this. The molten metal from the weld is cooling down, and solid grains of metal start to form. But right at the very end of this process, there are these super thin films of liquid that are still trapped between the solid grains. As the whole thing cools and shrinks, these weak liquid films get pulled apart, and boom, you've got a crack. It's kind of like trying to stretch pizza dough before it's ready. It just rips.
And we're not talking about some obscure, weird alloys here. We're talking about the absolute workhorses of the aerospace industry. Alloys like 7075 and 2024. They are so incredibly prone to this kind of cracking that for a lot of critical parts, the official procedure for welding them is, well, you just don't. It's not allowed. And that is a huge, huge limitation on designers and engineers.
But what if you could just sidestep the entire problem? What if the answer wasn't to try and get better at managing the melting and cooling, but to just get rid of melting altogether? This is where we get to a really radical and brilliant approach.
This is the game-changing question. If all the headaches, the cracking, the tearing, the weak spots, if they all come from that tricky phase where the metal goes from liquid to solid, then the most elegant solution is to just skip that phase entirely, to find a way to join metal while it stays completely solid.
And this is exactly how it's done. This is Friction Stir Welding, or FSW for short. You have this specially designed tool that spins really fast and it plunges right into the seam between two pieces of metal. Now, it doesn't melt it. Instead, the intense friction generates just enough heat to make the metal soft and plastic-like. Then, a pin on the tool literally stirs that softened material together, forging it into one solid piece. The best way to think about it is like kneading two pieces of clay together until you can't see the seam anymore.
So let's just put these two methods side by side. Traditional fusion welding melts the metal. That creates what engineers call a mushy zone, where you have liquid and solid mixed together, and that's where all those nasty solidification defects are born. Friction stir welding, on the other hand, just stirs the metal in a plasticized zone. By never actually melting the material, it neatly avoids all of those problems. It's a fundamentally cleaner process from a metallurgical point of view.
Now, just because we're not melting anything doesn't mean the metallurgy goes away. Oh no. In fact, this is where things get really, really cool. The unique metallurgical magic that happens inside the metal during FSW is precisely what makes the final joint so incredibly strong.
The secret sauce here is a process called dynamic recrystallization. The stirring action of the tool causes such intense, severe deformation that it literally breaks down the metal's old, large grain structure. And then, right in its place, brand new, tiny, perfect little grains are formed on the fly. This isn't just mixing the metal, it's like a complete rebirth of its internal structure.
So if you were to slice a stir weld in half and look at it under a microscope, you'd see three distinct zones. Right in the middle, you've got the nugget zone. That's where all that intense stirring and recrystallization happened. Around that is the thermomechanically affected zone, or TMAZ, where the metal was heated and deformed, but didn't fully recrystallize. And then on the outside, you have the heat-affected zone, or HAZ, which just like in a normal weld was only affected by the heat.
But let's really zoom in on that nugget zone, because that's the heart of the action. That combination of intense deformation and dynamic recrystallization gives you this absolutely beautiful, refined grain structure. The new grains are tiny and all roughly the same size. Metallurgists call this equiaxed. And why do we care? Because a fine, equiaxed grain structure is the hallmark of a super strong, tough material that's great at resisting cracks.
Okay, so that's a lot of science, but what does it actually do? How does creating this new, fancy microstructure translate into real-world performance that an engineer can actually measure? All right, take a look at this graph. It tells the whole story. This chart shows the hardness as you go across the weld. On the far left and right, that's our original super strong parent material. Now, as we move in toward the center, the heat from the process does soften the metal a little bit, so you see that dip in hardness. But then, right in the middle, in that nugget zone, that awesome fine-grained structure we just talked about kicks in and makes the material strong again, so the hardness actually recovers.
And here's a simpler diagram that really shows that classic profile. It's often called a W shape, and you can see why. You get two little dips in hardness on either side of the center, but then the strength from that recrystallized nugget in the middle causes the hardness to pop back up right at the weld line. This W profile is basically the mechanical fingerprint of a friction stir weld.
So, let's pull back for a second. What does all of this mean for the big picture? Well, this technology is much more than just a better way to weld. It really represents a completely new capability, a new way of thinking about how we build things with advanced materials.
I mean, the list of advantages is just huge. First, you completely eliminate solidification cracking. Gone. You also get rid of porosity from trapped gas because there's no liquid for gas to get trapped in. And while there's still some softening, it's often way less than with fusion welding. But here's the big one. It finally lets us join those high-strength alloys we used to call unweldable. On top of all that, it uses less energy, and you don't need any expensive filler wires or shielding gases. It's stronger, it's cleaner, and it's more efficient.
And that really leaves us with a mind-blowing question for the future. We started this journey trying to solve a specific problem with aluminum, but the principle, joining materials in their solid state, is so much bigger. Now that we can literally forge metals together without the destructive process of melting them, what other impossible combinations could we make? Joining steel to aluminum, creating new metal matrix composites? The door is now wide open to building materials and structures that, not too long ago, we could only dream about.